So here I'm using a simulation program called WaveMason to model what happens when we have a voltage source that's made up of a voltage that we can flip on to different types of signals. Here it's going to be just a DC signal that we turn on at some time, and a source resistor. It turns out that all voltage sources have some type of source impedance that's associated with them. So these two items together make up our voltage supply. Now the source impedance is going to go into a transmission line. Here we set up all three transmission lines that I can model as each being 50 ohms. So I have one long 50 ohm transmission line, and then I'm feeding this into a load, and here I've set up the load to be 50 ohms also. So at some time when I flip this open, we start getting this voltage wave that's going to travel down. So I've flipped a switch, I've set the voltage to go along the line. Now, because voltages don't travel instantaneously, because they travel at the speed of light or something slower than that, you don't have this voltage wave, banging against the load resistor at all the same time. It takes a while for this wave to propagate. So over the course of time, you're going to have that 1 volt pulse that's going to get closer and closer to the resistor until it actually reaches it. Now, you might ask, why is this 1 volt? Well, we have a 50 ohm source resistor that's hitting a 50 ohm impedance for the transmission line. So that 50 ohms divides by that 50 ohms. It's a voltage divide relationship, so that 2 volts becomes a 1 volt pulse that goes through. And then the next obvious question is, what is that source impedance? What does that mean? Well, the impedance of the transmission line could be like a coax line. And that coax line, if you were to put a multimeter probe on it, you're going to see that it's an open from a DC perspective. However, there's a relationship when that voltage wave is traveling down the line. There's a relationship between the voltage of the line and the current that's going down it. So when you just have this voltage wave traveling down the line before it's able to hit the resistor, before it's able to do anything, you can see that you have the 1 volt wave, and then you have 20 milliamp amounts of current, because we have 1 volt divided by that 50 ohms, that gives you 20 milliamps. So as this voltage wave goes down in the steady state, you see that we have that 1 volt and the 20 milliamps. So here we have the natural voltage division in the steady state case, not the AC, wave is traveling down, the wave is settled down. We have a voltage divider relationship where you have this 50 ohms for the source impedance and the 50 ohms for the resistor at the load. So you have the 2 volts across those, that's 1 volt at the terminus, and then 20 milliamps going through, because you have 2 volts divided by the 50 ohm plus 50 ohm, the 100 ohms. That gives you the 20 milliamps. Here, I'm launching a second wave. Again, it's a 1 volt, because we have a 50 ohm source that's going to a 50 ohm transmission line, 50 ohms all the way through, but in this time, I've shorted out the load resistor, so there's 0 ohms. But again, because at the time equals 0, as far as this wave is concerned, it's still got a 50 ohm impedance. So we have the 50 ohms over the 50 ohms for the 2 volt source. We have 1 volt, 20 milliamps, and that's going to travel all the way down the line. Now it takes this is a 0.16 meter line, so it takes about 5 nanoseconds for the light to travel down air-filled coax. It takes about 5 nanoseconds. So for 5 nanoseconds, we have no idea what's over here. Now, all of a sudden, we have a reflection off of this short. Now, we have a negative voltage wave that goes off of a short. We have a positive current wave that comes off of the short. So we actually have minus 1 volt reflection that sums with the 1 volt of the incoming, and that adds up to 0 volts. We've shorted out. Shorts means 0 volts at the termination. And we have now 40 milliamps because we have the 20 milliamps, and then we have a positive current wave that's summing with that, so 40 milliamps coming down. Now, at the source, we still have no idea what happened at the termination until about 10 nanoseconds later, when the voltage wave manages, the reflection bounces, hits again. And now in our steady state case, we see that we have 0 volts at the just after the voltage source. We have 0 volts here because it's shorted out through the transmission line. We have 40 milliamps. We have 40 milliamps at the current going through because we have the 2 volts divided by the 50 ohms. I'm launching a third case. Now, before I talk about what happens when we go into the infinite resistance case or the open case, again, I'm going to tackle, we're trying to answer here, what's the difference between resistance and impedance? Well, with the resistance, we have a voltage is equal to the current times the resistance, V equals IR. And that relationship holds true in the steady state. For an impedance, we still have that same sort of relationship. We have a voltage, 1 volt, is equal to the current, here 20 milliamps, times the impedance, which we've set to 50 ohms. So that relationship holds for the AC case, for the high frequency case. It just doesn't hold necessarily for the steady state case. So that's your fundamental difference between the impedance. It's still a voltage to current relationship that has to do with the waves as they travel down. But it doesn't necessarily mean that in the steady state case you'll have that same relationship, because fundamentally a coax or microstrip line, you still have just a 0 or very low impedance transmission line going through for the signal, plus you have some ground return that's a low impedance, low resistance state. So here we're going to show what happens when we have the open case. Again, it's the exact same at the start until about 10 nanoseconds later at the source side. You don't really know what's happened at the termination. It all looks the same. But here, going into an open, we have a positive voltage wave that comes down and sums to 2 volts, and a negative current wave. That negative current wave sums with the incoming wave and makes it 0. So this is about what you would expect in the steady state when you have a transmission line that's hooked up to an open. You have no current that's going to flow through, and you have 2 volts now because this 2 volt source has no current flowing through that resistor. So there's just the 2 volts that you have going all the way down the transmission line. For my last case, I'm going to run the 50 ohm transmission line again. Again, the start of the wave looks exactly the same for all cases, but the termination here is 30 ohms. So it's going to be higher resistance into lower resistance, which is mean a negative voltage wave traveling down and a positive current wave traveling back. And those current waves and voltage waves are going to sum up so that you end up with a steady state case of 0.75 volts and 25 milliamps. Now, this voltage is what comes out when you have the 50 ohms and the 30 ohms. So you would have the 30 over the 80 times the 2 volts, so it's 0.75 volts. It's just a voltage divider in the steady state case. And the 25 milliamps is the 2 volts divided by the 50 plus 30, the 80 ohms. So that gives you the 25 milliamps in the steady state case.